Okay, good morning, everyone. I'm going to present this work titled Multimodal Compact Bilinear Pooling for Visual Question Answering and Visual Grounding. Well, this work was presented in the VQA challenge of CVPR this year. And well, most of the content of this presentation is from the authors, so you can find it in this other link. So to start with the paper, I suppose that most of you know what is the problem of visual question answering, but in order to introduce it, what we want to do is to have a model that is able to learn from the inputs, which consist of an input image. For example, in the first one, we've got a picture of food, and also an associated question. In this case, would Sriracha make this tastier? And the model has to understand the picture and find precisely that information in order to answer it. So here you have some examples. What the authors of this paper tried to tackle in this work is precisely how to combine the information from the image and the information from the question in order to have a very good representation for answering this question. So if we suppose that we use a CNN for describing the picture, somehow we would have an information of let's say, the objects that appear in that image. And also, if we describe the question with a long short-term memory, we would have like the probability of appearing a certain type of words or concepts in that question. So what can we do in order to have correct merging of this information and extract the better answer we can? One of the things that they propose, well, that other works have proposed, in fact, is to just concatenate the output of these architectures. So if we do that, all elements could interact together, because then we would add a fully connected layer after this concatenation. But there is no multiplicative interaction between the elements of the image and the question. So it's difficult to learn the classification because there is no interaction between these elements. Another possibility would be to apply an element-wise multiplication, which in this case, there would be a multiplicative interaction, but not all elements interact with all elements in these vectors. So in this case, it's difficult to learn the input embedding, which means that it's difficult to make each of the components of each of the vectors mean the same than the corresponding component in the other vector. So somehow these models need to be combined in order to, and they have to know that each first element of the two vectors correspond to the same information, and the second element happens the same, so for all the elements. And the third possibility is to apply an outer product, so multiply all elements for all elements, but in this case, the problem would be that we have like 4 million different parameters if the vectors are of 2,000 components, more or less. So in this case, we would have interactions with all elements and multiplicative interactions also, but there are a lot of activations and a lot of parameters that are impossible to learn right now. So what they propose is to use this method, which is the outer product, but a compact version of it. So this way, having compacted the output vector to more or less 16,000 elements, we would preserve all these characteristics and have a lower dimension, a lower dimensionality vector. And how do they do this? So what they propose in this multimodal compact bilinear pooling is that they apply first a random projection of each of the two elements, each of the two vectors, And after this random projection is applied, they apply a convolution over the two vectors. And this, well, they apply more precisely the random projection, which is a specific version called count sketch, is to create a sparse vector from the source one, which, well, is based in a randomized selection of the components. And then the convolution, instead of applying a classical convolution vector by vector, they propose using the fast Fourier transform, then applying an element-wise multiplication, and then applying the inverse transformation. So, well, there is a theorem that says that applying a classical convolution is the same as applying the fast Fourier element-wise multiplication on the space of the frequencies. So that's why they apply this method. And this way, we would have a vector of 16,000 components if we have projected the vectors on that space. So if in the random projection we have set the 16,000 input. And with this in mind, they prepare their model. So they apply an Adam optimizer with that learning rate. They use the RefNet for describing the picture. And they use, as answers, they select the 3,000 most common answers. And then, well, they use the BQA challenge dataset and just use a training set for training, the validation, and then the test step for testing. And this is the overview of their architecture. So as you can see, they use the RefNet for the image and embedding and a two-layered LSTM for describing the question. And then when they have the two equally sized vectors, they apply the MCV for applying this multimodal compact linear pooling, what's it called. Then they apply two sets of normalization and just a fully connected layer and the final classification. With this architecture also, they try to measure how the length of the output vector of the MCV influences the result. And here you can see some examples. One could think that the longer the vector is, the result should be better. But in fact, there is some point in which it gets worse. So they try to set it to 16,000. And then also they compare their MCV method with other kinds of multimodal margins. So for example, if they just apply an element-wise sum of the image and the question vectors, they get 56% of accuracy, more or less. And with their method, they get 3 more points of performance. And well, they compare it with the concatenation, with an element-wise product. And well, it looks like their method works better than any other approach. And then, in order to improve even more the model, they try to apply some kind of attention mechanism. And basically, instead of just extracting one feature vector for the image, they get the convolutional feature vectors of the last convolutional layer. So they get a feature vector for each spatial location in the input image. Additionally, they replicate the vector of the question in order to match the size of the image, and then they apply the MCV on each local part of the image separately. So this way, at the end of the first softmax at the top row, what they will have is like a weight that measures how important a zone of the image is, depending on the question that they have. So probably, if the question talks about the salad, about some kind of salad, they expect that in the softmax, they will have a higher activation on the zone where the salad is, in this case. So after applying that weighted sum, what they do is to merge the information from the image, giving more weight to the zones that the question is pointing to. And then after this kind of merging, what they do is they apply again another MCV, which would be like a second layer of the MCV. So it's after the first one, and they just apply the final classification. And with this architecture, it's this case here, they get to 62.5 of accuracy, and then additionally they apply different improvements, like training not only with the training set but also with the validation set, and they improve a little bit more. Then they use an additional data set, an external one, which is called visual genome, for training with more data. They also see that applying, well, an ensemble method, so training different models with the same models but separate trainings, and having a majority voting at the end, they get another improvement. And finally, well, this is the result for another task, which is a multiple choice task, which instead of having to get an open-ended answer, they just have to choose from 4 different alternatives. So it's logical that in this case it should work better. And well, here you can see some examples of the attention mechanism. So in this case, if we have the question, is this person wearing a hat? And the ground truth is yes. And you can see that the method is able to guess that correctly, and it focuses on the zone where the head of the person is. In these other cases also, you can see that it's the same image, but different questions. In the first one, it's asking about what the animal is eating. In the second one, in the color of the shirt. But you can see that more or less it's able to focus on what is the question pointing to. And here, well, there are some wrong examples. In the first case, it asks about what is the product sold in the shop, and it guesses that it's clocks because, well, I don't know if you can see it properly, but there are some structures there that look like rounded, like clocks, and well, the result is wrong, but it looks like it has some sense. And here also it asks about which is a credit card company that is in the banners, and it focuses on the wrong banner. Instead of focusing on the MasterCard one, it focuses on the one at the left. So as a conclusions, the good parts of the method looks like it could be that it has that all elements can interact multiplicatively, and it offers a compact representation of this set of all multiple multiplications that could exist. And then it's easy to interpret thanks to the attention mechanism, and it's applicable to any multimodal tasks. So they apply it on visual question answering, but it could be useful for any other. And then the bad aspects, from my point of view, is that even though they call it compact and compared to the full bilinear model, it's still compact. But I think that having 16,000 features sometimes it's too much. And if we compare it with the concatenation of the summation of this element-one summation, so it's still very high. And then well, I've tested this model, and it's quite computationally demanding, giving this high dimensional representation. So that's all. If you have any questions?
Who won the challenge?
They won the challenge. And with a quite good margin. Yeah.
If you make the model more complex, so the decreasing will decrease, right?
Yeah, it looks like it decreases. Here, for example, they use 1,000 features instead of 16,000. And if we compare it to other methods, so here they get 58.4, it would be a little bit below the element-wise product. So it looks like it's not that powerful in that low dimensionality. So we have to, well, there's always that trade-off. But and if we compare it, if we use the same number of features, which would be this case, 2000, here we've got 58.8. It would be, compared to the element-wise, it would be just to 0.2 difference. So in that case, it's not that much.
Can you please repeat now what they computed the random project and multiply?
Sorry?
The first part.
Yeah.
You said they first do a random projection of the vectors and then they multiply them.
Yeah.
So this is just the way they implement this. And they say why they do this way. Implement this way.
Well, they apply the random projection because they want to fix the size of the output.
So this is to do an embedding of the first feature vector and the second feature vector?
No, this is for combining the first feature vector of the image to the feature vector of the whole question.
Yeah,
so what they do?
We have a linguistic vector, if you want. The one is a visual vector.
Yeah.
They come from CNN. So you should embed these two vectors in a common space.
Yeah, and somehow, well, I think that what they try to do is to find the correlations between the two vectors. So if the question is talking, as I said before, if it's talking, for example, about the salad, then the vector of the image corresponding to the zone where the salad is should have a higher activation somehow. And if the question has nothing to do with the image, then the output should be quite, well, should have lower activations. That's my intuition.
In general, what people they use, what is they use for doing this kind of embedding?
Well, the techniques that they use are these ones that they compare here. So it's just applying a summation, element-wise summation, element-wise product, concatenation. So it's quite straightforward. So to concatenate, it's just doing this. It's this case. So they get both output vectors and they just apply something else.
Yeah, the second one.
This one is the element-wise multiplication. So another option would be to do this.
Because I mean, they are not the same meaning, the vector, the linguistic vector.
Yeah, the thing is that's why they say that it's difficult to learn that embedding.
Yeah.
Because this way, if the method is powerful enough, then the LSTM and the CNN should somehow learn that they have to output the same information from the first value, the same one on the second value. But it's, well, I suppose it's difficult to do that.
I have one personal curiosity. This randomized this projection, random projection, it doesn't seem to me very like. Well, my question is that is there any other better way to do this projection to lower the dimension, but not using random projection? Because random projection is very random.
Yeah.
It's very like could be anything.
They don't propose any alternative, but I suppose
Do you know of any other maybe? No.
I don't know, but yeah, probably there should be some more clever way of doing that. We have to think about it.
Maybe we can think about the reasons. So this is computationally expensive?
Yeah, well, we found maybe it's because, well, we are trying to use the GPU because for training it's much better than using the CPU. But I think that the fast Fourier transform is not optimized for using the CPU. So
basically, what cost a lot each operation?
I think that it's the fast Fourier transform because the GPU is used to work with just multiplications of matrices and things. And well, I think that this is not what it's supposed to do the GPU. So, and that's why we don't understand why they use the fast Fourier transform instead of a normal convolution. So if they say that they substitute the normal convolution of two vectors for this. And well, we have just implemented the same method, but just with a normal convolution. And we have not tested it completely, but it looks like it works faster.
So the convolution, the formula you have there, right?
Yeah, well, this is, they say that applying the random, this symbol is a random projection, applying the random projection to the two vectors after applying the outer product is the same as first applying the random projection separately and then multiplying the, well, that's not a multiplication, that's a convolution, convolving the two informations. And
there, X and E, they are been randomly projected already?
And here?
Yeah.
Yeah, here they are first randomly projected, that is what they apply, and then they apply the convolution. And in their case, furthermore, they don't apply the usual convolution, but the convolution on the space of the frequencies with the FFT. So, as I was saying, from the FFT part, I don't know why they choose this way of implementing it instead of a normal convolution. They don't say why.
This is based on the research around the paper, no? Because
Yeah, this is another paper. Yeah.
Any more question?